Hello and welcome to Project 152, your weekly specialist exam prep. Now every week we go through past questions from the QCAA. The goal is to get through every one of the 152 questions that the QCAA has ever done. Now this is week 20 and we're going to go through the solutions. All of these questions are tech free, so put your calculator away. Let's get started. So this question is designed just to find out whether you know what all these symbols mean. So let's go through it. According to a recent census, the mean hours worked per week by all Australian workers is 35.6. Let me just write that down. The population mean, coming from a census, right, is 35.6. Okay, and then it says a mean of 36.1 hours worked per week is calculated from a random selection of 500. So that is a sample mean, and that value is 36.1. Okay, so these are both means, right? But one is the population mean. They calculated the mean from absolutely everyone. The next one is just a sample mean. And so we need to know what these symbols mean. One of these symbols must mean population mean, and one of these symbols must mean sample mean. Let's look at the syllabus. Boom, here. And I'm going to take a look here. It says use lowercase x hat and s to estimate mu and sigma. All right, lowercase x and s is using our sample mean and our sample standard deviation. And if we know a sample mean and a sample standard deviation, we can estimate the population mean and the population standard deviation. So these symbols belong to populations, these symbols belong to samples. So I should be able to find my answer now, right? Because I'm going to use these two, which are my mean symbols, and I'm going to look for that one being 35.6 and the next one being 36.1. There is a small thing that I want to talk about in the solutions here, and this is this uppercase X. What's uppercase X? It is the sample mean as a random variable, right? So remember that your means, depending on which sample you take, your mean's going to be different. Sometimes your mean's going to be here, sometimes your mean's going to be here, 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 here. Uppercase X represents the random variable that is those differences. This one, this one, this one, this one. Okay, finally, we have an answer. It is C, lowercase x, so that's the sample mean, is 36.1. And mu is 35.6, our population mean. Fairly straightforward question. Next. So another little statistics question here. Let's read from the bottom. Based on this sampling, the standard deviation of the distribution of the sample mean. So the standard deviation of the sample mean. If I had a formula for that, that would be great. Here we go. Standard deviation of the sample mean. All right, so let me just write down that formula. Standard deviation of the sample mean is S, and it's going to be equal to sigma over root n. And if I knew those values, that would be great. So this is the standard deviation of the population, and we have a population of packets of sunflower seeds. All right, the number of sunflower seeds in each packet is known to be normally distributed with a standard deviation of 100. So standard deviation of 100 over, and then a worker counts the number of seeds in a random sample of 4 packets. So we're taking a very small sample here, just 4 packets. So root 4. No calculators, so it's 100 divided by 2. Square root of 4 is 2, which is 50. There's my answer. The answer's 50. Nice little fun one here. Go looking for your formula, and away you go. Celebrate. Alright, so I'm a big fan of this question. I think it's a fun one because if you're clever about how you work through it, it's really nice. So we've got an object here, right? And it's being pulled by 2 forces. It's being pulled by a force in this direction, and it's also being pulled by a force in that direction there. Now the forces are equal, 4 newtons in that direction and 4 newtons in that direction. Now what's going to happen? Well, if you were 2 friends pulling this object, it's going to move in that direction, right? The movement of this object is going to be equal to the sum of the forces on the object. Now, a lot of people might try to break this into components and do it that way, but I'm going to work solely with triangles. So there is this force, like I said, of like 4 newtons moving in that direction. Let's just fix that up. And then if I've got a vector and I want to add another vector to it, it's the old like tip and tail thing. So vector plus vector. Now, because of the angles they've chosen, we get an equilateral triangle, right? That should be easy to see, I hope, because this is a 30-degree angle here. This is a 30-degree angle here, which pushes a 30-degree angle to there, and that's a 30-degree angle. It's an equilateral triangle with lengths of 4, 4, and of course, 4. So, incredibly, people pulling 4 newtons in this direction, 4 newtons in this direction, we end up with 4 newtons of force acting in this direction. So it's tempting here to make the answer C, 4. This is kind of a really good distractor, but we're not asked about the force acting on it. We're being asked the magnitude of the acceleration. So we know that force is equal to mass times acceleration. We know that the force being acted on, we've got 4 here. We know the mass of the object is 2 kilograms, and what we want to know is the acceleration. So 4 over 2 equals A equals 2 meters per second. Our answer is A. Very, very nice. Celebrate. Okay, let's move on to some short response questions. So this question's quite kind because they really tell you everything that you need to do. The expected value of an exponential random variable x, blah, 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 is this rule. All right, so we're given a rule, and then we're told use integration by parts to figure this thing out. So we're told integration by parts, formula sheet, there's integration by parts. Express your answer in simplest form. All right, so let's go for it. We're told that the formula, the expected value, is going to be equal to the integral between infinity, that's a terrible infinity sign, and 0 of x lambda e to the negative lambda x with respect to x. And we're told we've got to use integration by parts. And so we can split this into u and dv dx. And so we need to determine how to split that up. Now, if you sort of look forward in your mind, you should see that it's a good idea to put all of this together as a single piece, and it's a good idea to put all of this together. So why is it a good idea to put this all together? Because I could have grouped that lambda with the x. The reason is because I've got a lambda and a lambda here, and I know that when I'm integrating, deriving exponential functions, they're going to end up like above or below each other and maybe cancel each other out, do something like that. Okay, so one of these is going to be u, and one of them is going to be dv dx. How do I determine that? We use our acronym DETAIL. Now, if you're not familiar with DETAIL, the way to work it is it tells you what dv dx should be. Now, dv dx should be exponential. If you can't find an exponential function, find a trig function. If you can't find one of those, find an algebraic function or an inverse trig function. And lastly, find some kind of log function. Now, here, I can see an exponential. And so exponential is what my dv dx is going to be, or what I tend to call v dash. So my v dash is going to be lambda e to the negative lambda x, which means that my u is going to be simply x here. U is equal to x, which means that u dash is equal to the derivative of that, which is 1. Finally, I need to know what v is, and v is going to be equal to the integral of this. Okay, the integral of that is going to be equal to lambda divided by the derivative of this, which is negative lambda, e to the negative lambda x. The lambdas cancel out and I'm left with negative e to the negative lambda x. Let's put that up there. And now that I've got my nice little table here, always important to do this, I can use this formula. So it says the integral of u dv dx is equal to u times v, so that's x lambda e to the negative lambda x, and then minus the integral of, and it says v du dx, or v u dash. So u dash is 1. So 1 times v. And v is this bit here. Negative e to the negative lambda x with respect to x. Now I've left all my terminals off this because I'm integrating between 0 and infinity. So 0 and infinity need to go here. And this piece out the front here, that's also between 0 and infinity. All right, so I can do two things at once here. Let's deal with this between 0 and infinity. Now to do that, I'm subbing infinity in for x, and I'm subbing in 0 for x and subtracting 1 from the other. All right, so there is quite a bit going on here, so let's just get rid of our little formula. We don't need that anymore. Okay, so what I've done is sub infinity into this and sub 0 into this, and then I've left that how it is. Now I am going to change some things in a second. Okay, what do I notice? First of all, I notice this bit here, minus 0 times blah, 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 blah. Well, 0 times anything is going to be 0. So that's simple. This is a very simple minus 0. Okay, what about this next bit here? This says infinity, and so we're thinking limits and things like that. Infinity times lambda times e to the negative lambda infinity. Now, e to a negative is the same as 1 over e to whatever that happens to be. So I can rewrite this as infinity times lambda over e to the lambda infinity, removing this bit right here. Okay, now that I've rewritten it like that, what does it mean? Right? What we have is a very large number divided by a very, very, very large number. Now, this is a very, very, very large number because it's e to the power of infinity, right? Now, as you divide something by a larger and larger and larger and larger and larger number, if you divide something by 1 billion, what you get is a very small thing. The limit of this as we approach infinity is 0, right? So that's 0. This is still 0. Now, this bit here, we can work with this now because this is really all that matters. So the integral of that is going to be, we need to be a little bit careful here with like our negatives. It's going to be dividing by negative lambda, so negative 1 over negative lambda e to the negative lambda x, and we're going between infinity and 0. Okay, and now all we need to do is finish this off. Feels like it needs a little bit of explaining, so let's go. We've got negative, and then we've got negative, negative, right? So that's positive. Negative 1 over negative lambda, that's positive. So it's going to be, let's just leave a negative out the front for now, and we'll deal with all of this stuff at the end. All right, so we have 1 over lambda, and then we've got e to the negative lambda x. And remember, e to the negative lambda x, we talked about this here. It's the same as e to the lambda x, and x in this case is infinity. Okay, so I'm putting that in there, and then I'm doing, again, 1 over lambda e to the lambda 0. Okay, that feels pretty good. Now, what do we have here? 1 over a very large number. So, again, we have 0, and then we're subtracting 1 over lambda times e to the lambda 0. So e to the 0, right? Because lambda times 0 is 0. E to the 0 is 1. So 1 over lambda times 1. 1 over lambda. Okay, I am finished. This is equal, minus 1 over lambda. My final answer is 1 over lambda. Let's be very, very clear here. What was the question asking us to do? It was saying the expected value is given by this formula. Use integration by parts. I did that. I did a bunch of calculations. Express your answer in simplest form. I've made it all the way down to e to the x, or ex, the expected value, is equal to 1 over lambda. Celebrate. So a really fantastic question here. Complex unfamiliar, last question on the exam. If we read the bottom, determine the rate at which the depth of liquid. So immediately I'm seeing three-dimensional objects, determine the rate. I'm thinking related rates. But then I'm also seeing this phrase, rotating the curve. So then I'm thinking volumes of solids of revolution. So this is a classic example of a maths teacher taking two ideas and smushing them together into a complex unfamiliar question. That's quite often how math teachers write complex unfamiliar questions. Let's just move things around a little bit. Okay, no change. Now, before I can deal with the rate at all, I really think I need to figure out this volume of solid of revolution. Now, it's being rotated around the y-axis. I do have a formula sheet, volumes of solids of revolution, but rotating around the y-axis, it's the bottom formula. So let's zoom in on that. Now, rotating around the y-axis adds a complication because we need a function of y, but at the moment I have a function of x. So we're going to have to rearrange that formula. So a quick bit of rearrangement. We're going to go y plus 1 equals 4 over 8 minus, that's an x. And then I can do, so I can cross multiplication. I can move the 8 minus x to this side. And we get 4 over y plus 1. And finally, I can take sort of this x, move it over here to add x to both sides. And I can go 8 minus 4 over y plus 1. Beautiful. This is important stuff. This is a function in terms of y. It's a function of y, and that's what we can put into our formula. All right, so I've pretty much done the whole formula here. V equals pi, and then an integral, and then the function. Don't forget to square it with respect to y. What I haven't put in are my bounds, and you need to be really careful here. Some people will look at the question and see 4 and 7.6 and think that those are our bounds here, right? What do the numbers 4 and 7.6 represent? They represent the x-coordinate here and the x-coordinate here, right? So 7.6 is about there and 4 is about there. But when we're rotating around the y-axis, we're not interested in the x-coordinates. That's not what A and B are referring to in our formula. A and B are referring to the y-coordinates here and like the y-coordinate like here, right? If that's like level with the top. Okay, so those two values there are what A and B represent. Now, if you sub 4 into this, right, 4 over 8 minus 4 minus 1, you get 0. And so this value, and that makes sense because you can see it's drawn that way, 0 is going to go on the bottom. Now, it's also tempting to go, okay, I want the volume of the entire thing, but this is going to be like a related rates thing where we're filling this object over time, right? And so the amount of volume in our object is a variable. It changes as we fill it. So let's just call this H, because it could be here, it could be here, it could be here, it could be here, etc., etc., etc. So talking about that H, up, that feels like change, right? Feels like a rate of change. Maybe I'll just leave this for a second and think more about what I'm actually trying to get to at the end. Determine the rate at which the depth of liquid is increasing when the depth of liquid reaches 1/3 of the height of the bowl. Okay, now rate at which the depth, or rate at which the height, because depth, height, okay, same deal. The rate at which the height is increasing with respect to time. Okay, now it's definitely a related rates question. So the way that I tend to sort of do those is something a bit like this. Okay, and what's the intermediary variable between H and T? Usually there's a hint here. The bowl is being filled with liquid at the rate of 7 pi centimeters cubed per second. Okay, that is a rate of volume per second. So volume. Okay, this is really good. dHdt equals dHdV times dVdt. And not only that, but I already know the volume with respect to time it's equal to 7 pi. So what do I need? I need a relationship between h and v. And I kind of do have a relationship here between h and v. If only I could find some way to get this relationship between h and v a little more clear. So when you see this, it's going to be tempting to think, okay, obvious, I'm going to integrate, and then I'm going to sub h in, I'm going to sub 0 in, subtract one from the other. Much nicer way to go about this. And it's going to be a little bit confusing, perhaps. All right, so we've got v equals pi, the integral between h and 0, blah, 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 with respect to y. Now, look, I've got this like dh dv, so I want the change in v. So, forgetting about the definite part of our integral for a second. dv dy, so the change in v with respect to y, because I'm deriving, and I've got an integral here, derivatives and integrals are the opposites of each other, I've undone the integral. So dv dy equals pi 8 minus 4 on y plus 1 squared. But I'm not integrating, or I don't want to derive with respect to y. I want to derive with respect to h. We can replace the y's with h's. Now, depending on how much work you've done on like the theoretical nature of the fundamental theorem of calculus, this either feels fine or it feels like absolute nonsense. So for those of us who feel like this feels like nonsense, let me just show you a little bit of stuff, like a little bit of teaching to get you through how I'm getting from here to here. So here's our little sidebar. V equals pi, so same sort of formula, but instead of all this nonsense, I've just called it f of y squared. Now, for the purposes of what I'm about to talk about, f of y squared, that's just another function. So let's just call it like g of y, and that way we can get rid of the squared, and we can talk at a much more basic level. So far so good. Now, if we want to find the definite integral here, we're going to have pi, and then we're going to sub h in to not lowercase g of y, but uppercase g of y, the integral of whatever g of y was. So we're going to sub h in there, right? And then we're also going to have g of 0 subbed into there, not added together, subtracted from each other. So there's our new volume. So far, so good. One more step here, and I've just expanded those brackets, pi times capital G of h minus pi times capital G of 0. Now, dv dh, so finding the derivative of this, dv dh, what happens? Well, capital G of h, we undo the capital G of h, and we end up at lowercase g of h. Lowercase g of h times pi. That's going to be the derivative, right? So pi times lowercase g of h. And then what about this? Well, g of 0, that's not a function anymore. That's an actual number, right? If you sub the number 0 into g, this is a number, which means all of this is a number. And the derivative of a number is 0. Boop. So we end up with dv dh equals pi lowercase g of h. Now remember, I said, hey, to make this easier, let's just say f of x squared is f of y squared is g of y. So now I can put that back in there. So g of y is not g of y, it's f of x squared, which is exactly what we did there. So, okay, sidebar over. We're going to get rid of this. If you are in this kind of situation, you can immediately undo your definite integral if you've got 0 and some like variable up the top, right? Or even any number. It doesn't have to be 0. It can be 2 or 5 or 7, because if I put 2, 5 or 7 in here, I'm still going to end up with a number, and the derivative of that's still going to be 0, so I'm still going to end up in the same position. So you don't have to hope that that's a 0. It can be absolutely anything, but all of a sudden, dv dh, and we've got this nice little bit here. Okay, sidebar over. So now that we've got this magical little thing here, we can refer back to where we were. We don't want dv dh, we want dh dv. So reciprocal, reciprocal. This is fantastic because now I know dh dv is equal to this, which means that I can come up with a single dh dt because I've got dh dv now and I've got dv dt now. So I'm going to take this, I'm going to bring it down here, I'm going to sub that formula into it while I'm at it. All right, so amazingly, dh dt is equal to 7 pi times 1 over all of that. So we get 7 pi over all of this, and amazingly, our pi's are going to cancel out, and we've got 7 over 8 minus 4 over h plus 1 squared. Looks pretty good. So we're nearly done because we've got a function that tells us the height at any given time, or the rate of change of the height with respect to time. We've got this function here, and it says determine the rate at which the depth of liquid is increasing when the depth of liquid reaches 1/3 of the height of the bowl. So here's my bowl, here's 1/3 of the height of the bowl. So the question is, what is that height? Well, I don't know what 1/3 of the height of the bowl is, but I know here is 0, and I actually don't know this one yet either, but if I knew that one, I could just divide it by 3, right? And I know that the bowl is between 4 and 7.6. All right, so that point there is 7.6, but I don't know the y value. But thankfully, I do have a function that will let me find that y value, this one right here. So if I sub 7.6 into this, I'll know what the y value is at that time as well. Okay, so what do we have? We've got 4 divided by 0.4. 4 divided by 0.4 is 10. 10 minus 1 is 9. The height of the bowl is 9. So the height that we want, 1/3 of the height, 1/3 height, is equal to 9 over 3, which is 3. Okay, so we want to know at what rate the height is changing, or determine the rate at which the depth of liquid is increasing when the depth of liquid reaches 1/3 of the height of the bowl. Okay, so if I know h is equal to 3, I'll know the rate at which the height is increasing. So let's sub 3 into our height with respect to time formula. So I'm letting h equal 3. The rate of change of the height with respect to time is equal to 7 over 8 minus, that's 4 over 4, so 8 minus 1, that's 7. So 7 squared is 49. 7 over 49, 1 over 7. 1 over 7 is my answer, but I probably need some units here. Let me hunt for some units. I have determined the rate at which the depth of liquid is increasing. We've got seconds and we've got centimeters. So 1/7 centimeters per second. It's a big question, so it's worthwhile talking through what we did. Okay, let's just recap very, very quickly. We had a function, but we were rotating around the y-axis, so we had to rearrange it to make x equals something. And then we said, okay, what's the volume of this bowl at any given height? The volume is equal to this, between 0 and whatever that height happens to be. Then we had to make this leap here, which some people are going to sort of be a bit weirded out by. And the reason we started working towards this was because we knew we needed it. We knew we needed dH/dV or dV/dH. So we did that, we got to here, and then dH/dt comes from this nice little formula here. Great. We needed to know what 1/3 of the height was, relatively straightforward compared to the other stuff, and then we let h equal 3 in our rate of change formula, and we get a final answer. Worth a celebration. So that has been week 20 of Project 152. Thanks very much for hanging around. Next week, go to the link in the description now. You can check out next week's questions. I'll see you then. It'll be tech active. Probably going to do a bunch of stat stuff, I imagine. Catch you then.